Okay, so let's now move to space-time. So say we have a metric with only diagonal terms. We won't worry about what the actual values of these metric terms are, but such that we have g0, 0, and that's, well, dx0 squared plus g11, dx1 squared plus g22, dx2 squared plus g33, dx3 squared. And say that x0, x1, x2, and x3 are time r, theta, and phi coordinates. And let's look at the geodesic equation. Let's look at a component. And let's make contact with Newton's law of gravitation. So let's say that dr equals d theta equals d phi equals 0. So we're at some fixed location, and ds squared, well, that's just the tau squared, and that's g naught dt squared. And so basically the rate at which 2 times vary with respect to each other, or the square of dt by d tau, is the inverse of that component. And so basically this component carries the curvature of time in it. Right, so this would just be equal to 1 if there were no curved time here. So we're going to show that curved time is really what determines, is really how we describe, from the perspective of general relativity, Newton's law of gravity. So let's, therefore, we're looking at, let's look at second derivative of x1, in other words, second derivative of r. All right, so we're at some location r, and we're looking at the acceleration in that coordinate with respect to proper time, and we know how to compute these, right? We need the connection coefficients, gamma 1, beta gamma, dx gamma d tau, dx beta d tau, and this is, well, it's 2 derivatives in x1 tau plus gamma 1, 0 gamma dx gamma d tau dx 0 d tau plus gamma 1, 1 gamma dx gamma d tau dx1 d tau plus well, we're going to write this all out, at least up to a certain point. Gamma 1, 2 gamma dx gamma d tau dx2 d tau plus gamma 1, 3 gamma dx gamma d tau dx3 d tau. Well, it's not obvious that we just need the 1, 0, 0. So this is equal to d2x1 d tau squared plus gamma 1, 0, 0 dx0 d tau, dx0 d tau, curvature of time, plus gamma 1, 0, 1. Now we get into spatial derivatives, but these are all 0 because we're not moving in the spatial direction. dx0 dx tau plus gamma 1, 0, 2 dx2 dx tau dx0 dx tau plus gamma 1, 0, 3. You sort of see that you always have a spatial derivative, dx3 d tau, dx0 d tau, plus gamma 1, 1, 0, dx0 d tau, and then you have the spatial one, dx1 d tau, plus gamma 1, 1, dx1 d tau, dx1 d tau, plus gamma 1, 2s, gamma 1, 1, 2s, gamma 1, 1, 3s. These will all bring in dx2s and dx3s with respect to tau. So we can sort of see that, we have some dx0s with respect to tau, but we'll have other terms as well that involve the spatial derivative. So plot dot dot dot, all of these things will be 0, and therefore the only thing that we care about, right, because we want to consider a situation where are we? So let's be precise here. dr by d tau equals d theta by d tau equals d phi by d tau. That's equal to 0. And so this is the only term that will survive. So that's the one we need to explore. So we get second derivative of x1 in tau minus sorry, I'm already evaluating that. I'm making a mess here. So our previous equation that we were just looking at, we have plus gamma 1, 0, 0 dx0 by d tau, dx0 by d tau. And this is equal to, this whole thing is equal to 0. But this is the only term that survives. So that looks like second derivative of r in tau plus gamma 1, 0, 0 dt by d tau squared. That's equal to 0. So we need gamma 1, 0, 0. So gamma 1, 0, 0 is equal to we go back to our expression for the metric GB1 dG0B in x0 plus dG0B in x0 again minus dG00 xB, and we can see that because the off-diagonal terms are all 0, only the b equals 1 term survives. So we have 1/2 G11 times dG01 respect to x0 plus dG01 minus dG00 with respect to x1. And so these are 0, of course, and so we have minus 1/2 g11 dg00 with respect to x1. And so our geodesic equation is second derivative of r in tau is equal to 1/2 g11 times g00 with respect to r. So this looks like a gradient kind of thing, and that's going to end up giving us the 1 over r squared expression for the acceleration due to gravity. But the key issue is that we see that in the low velocity limit, we recover this force equation, acceleration equals to force, via the curvature of time.